written expression, it's easy to calculate the dot product. This is our f of ti star, and what we have down here is our delta s sub I, so that this equals, not sure I can get this all on one line, but let's try. The f, which is the sine of 2 pi t sub I star times the I vector, no way it's going on one line, but plus the cosine of 2 pi t I star times the j vector, dotted with our delta si vector, which is 2 pi, which is just a constant, can be brought out in front, multiplied by negative sine of 2 pi ti star plus the cosine of 2 pi ti star multiplied by j, and that then equals 2 pi times negative sine squared of 2 pi ti star plus cosine squared of 2 pi ti star. Now, without digressing into the details of the integration, which have been covered fairly well in previous notes, I'll note, and there's a simple symmetry argument that also shows this to be true, that this equals okay, I have an error which I can fairly easily correct. Our delta Si is this, but it's then multiplied by the delta t, and I left off the delta t. I just wrote down the r prime evaluated at ti star, so we need a delta t down here, meaning of course that we need a delta t on this term and a delta t here. Now, I'm going to hand wave a little bit. This is our expression for the f of t dot delta s interval corresponding to a time lapse of delta t, and this is on the ith interval, evaluated at the sample, everything evaluated at the sample point. To get the sum of these terms all the way around our circle, we have to follow the parameterization of our circle. We would have to sum over our partition, which means that we have to sum t values from 0 to 1. That by now should be a familiar process, and you should therefore hopefully understand that this approaches the integral, and I didn't tape down my correction. This approaches the integral from 0 to 1 of the expression that we get, just letting the intervals approach, the length of the intervals approach 0, so that the delta t approaches 0, and the ti star is trapped near whatever the value of t is, giving us 2 pi times negative sine squared t plus cosine squared t dt. And now, it's no miracle. We can easily assert that this equals 0. In the first place, we've seen integrals of this nature, and in the second place, the integral of the sine squared around a complete circuit. And good thing I started talking about this, because I forgot the 2 pi in front of the t in both of these terms. So the t going from 0 to 1 doesn't describe a circuit, complete circuit around the circle with this expression, but we can fix that. Okay, I've made the correction. I've had to write things a little bit smaller. But again, we've seen integrals of this nature. The sine squared goes around a complete circuit. The cosine squared of the angle as it goes around a complete circuit. And by symmetry, if you average the sine squared over a complete circuit and average the cosine squared over a complete circuit, they're equal. So that integrating the negative of the sine squared plus the cosine squared has to give us 0. They're also identities and so forth. We can replace the sine by 1 minus cosine squared, giving us 1 plus 2 cosine squared, and leading to an expression we can trick into an integral, or we could integrate each of these by parts. By whatever argument, this integral turns out to be 0, and the integral of our function around a circle is 0. And recall that for this function, the curl was 0. Recall that the curl of f was 0 at every point. So we've actually illustrated the process of developing a line integral, and we've addressed the assertion that the integral of a function around a small circle containing a point is somehow an indication of the curl of that function.